Hello everybody, let's solve the JAM 2020 chemistry question paper today from question number 21 to question number 25. Moving to question number 21, the complex which does not obey 18 electron rule is. Four transition metal complexes are given as options, and out of these four, you have to choose the complex which does not obey the 18 electron rule. So to find that, you need to first learn how to count electrons for complexes. So for doing that, the first step is to find the oxidation state of the metal. The transition metal, you find the oxidation state for the transition metal, and then based on that you count how many d electrons that metal will have, and to that you will add the number of electrons donated by each of this ligand to the metal. So basically it is just the sum of the electrons for the metal, the valence electrons for the metal, plus the number of electrons donated by each of the ligand to that metal. And additionally, if the complex has any charge, overall charge, for example, like this in iron case, the iron carbonyl complex, the complex has an overall charge of 2 minus. So in that case, you will have to take into account that also you will have to add 2 electrons to the overall electron count. Okay, so this is how you count electrons in the oxidation state method. There is another method which is called the neutral atom method. You can use that method also to count electrons, but here I will be counting via the oxidation state method. So let's start calculating the number of electrons for each of this complex, starting from the cobalt carbonyl complex. So we find the valence electrons for cobalt. So cobalt is a 4s2 3d7. 4s2 3d7, that means there are 9 electrons. You can say there are 9d electrons. So 9 electrons, and there are 2 cobalts. 2 cobalts. So you will have to multiply 9 multiplied by 2. So 9 multiplied by 2, then you have to add the number of electrons donated by the carbonyl ligand. Each carbonyl ligand donates 2 electrons each, and there are 8 of them. So plus 2 multiplied by 8. And then to that you have to add an extra 2 electrons, because this cobalt complex, there is a cobalt bond in this complex. There are 2 cobalt and there is a bond between the 2 cobalts, so which involves 2 electrons. So you have to add those 2 electrons also, and then the whole thing you have to multiply, you have to divide by 2, because you have to find the number of the number of electrons around each cobalt metal. Each cobalt metal, you have to find how many electrons are there. So the overall count you divide it by 2. So 9 electrons for each cobalt multiplied by 2, because there are 2 cobalts, plus 2 multiplied by 8, because there are 8 carbonyl ligands donating 2 electrons each, plus 2 because these 2 electrons are involved in the cobalt-cobalt bond. And the whole thing you divide by 2, because you have to find the number of electrons around each transition metal, that is around each cobalt. So you divide that by 2. So you get 18 electrons for each cobalt. Okay, so that means this complex obeys the cobalt carbonyl complex obeys the 18 electron rule. Moving on to the next complex, which is the iron carbonyl complex. Here you count for iron. There are no negative anionic ligands. There are no anionic ligands. So you can say iron is in a neutral state. There is, because there is no anionic ligand. So iron is, the configuration is 3d6, 4s2 3d6. So 4s2 3d6, you can say 8 electrons for iron, 8 electrons, and 2 electrons donated by each of these 4 carbonyls. So plus 8 plus 2 multiplied by 4, and then plus 2, because the overall complex has a 2 minus charge. So you add 2 for that. So while after doing that, you will see that you will get 18 electrons for this iron complex also. Moving on to the manganese complex. In the manganese complex, if you see, there is a hydride ligand and carbonyl ligand. Now the carbonyl ligand is neutral, but the hydride ligand is a -1 -1. It's an anionic ligand. So this is an anionic ligand. That means manganese is in a +1 state. So manganese, the configuration is 7. that is 4s2 3d5, so 7 valence electrons, but because it is a plus 1, you remove 1 electron, so that gives you 6 valence electrons for manganese. Now 6 plus the hydride ligand donates 2 electrons, so you add 2 to that, and then 2 from each of these 5 carbonyl ligands. So you add 2 multiplied by 5, and when you do that, you will get 18 valence electrons. Moving on to the ruthenium complex. The ruthenium complex, as you see, has 4 different types of ligands. The cyclopentadiene ligand is an anionic ligand, monoanionic ligand. The chloride is also a monoanionic ligand. Carbonyl is a neutral ligand, and the diphenylphosphine is also a monoanionic ligand. So there are 3 monoanionic ligands. The cyclopentadienyl, the chloride, and the diphenylphosphine ligand are all negative ones. 3 monoanionic ligands. So that makes the ruthenium plus 3. It's in a plus 3 state. So if it's in a plus 3 state, what is the number of electrons for the ruthenium metal? See, the configuration for ruthenium is 4s2 3d6. It's a 4s2 3d6, so that means it's an d8. You can call it an 8 valence electron metal. But out of this 8, 3 electrons are gone. It's in a 3 plus state. So that means you can count 5 electrons for ruthenium. 5 electrons for ruthenium plus the cyclopentadienyl ligand donates a 6 electrons. It's a 6 electron donor. So plus 6. The chloride is a 2 electron donor plus 2. The carbonyl is again a 2 electron donor plus 2. And the diphenylphosphine is another 2 electron donor. So you add that. When you add all this, you will get that you will only 17. It's not obeying the 18 electron rule. So the complex which does not obey the 18 electron rule here is the ruthenium complex. Okay, so here is a table in which will help you to count electrons in the oxidation state method. So here it shows how many electrons each of these ligands donate in for counting in the oxidation state method. So you have the 2 electron donors here, the list of 4 electron donors here, and this list of 6 electron donors here. Okay, moving on to question number 22. The solid state structure of hydrogen fluoride is. So here basically they have shown the hydrogen bonding in hydrogen fluoride. So when you look at these 4 options, the first option is definitely wrong because you cannot have a linear arrangement like this. The fluorine atom has 3 lone pair of electrons which is arranged around the fluorine, and one of those lone pair is what is attracting that hydrogen from the other hydrogen fluoride molecule. So it can definitely not be linear. It has to be bent because around fluorine the bond pair and the 3 lone pairs are in a tetrahedral arrangement. So the electron pair which is available for hydrogen bonding will be at an angle. So it cannot be this linear like this. So option A is wrong. Now in these 3 cases, you will see that this option C and option D is wrong, because in the case of a hydrogen bond, the hydrogen has to be between the 2 fluorine atoms, and the angle which is formed by the electronegative atom, hydrogen, and the electronegative atom is almost linear. It is almost 180 degree. Now here in option D, you see it is not linear because it is at an angle. So option D is wrong. Option C is also wrong because here you have a fluorine between 2 hydrogens. It is not like that. You should have a hydrogen between 2 fluorine atoms, and the fluorine, the angle between the fluorine, hydrogen, and the fluorine has to be almost linear. So that is how it is in hydrogen bonding. So in hydrogen bonding, the angle between the electronegative element, hydrogen, and the other electronegative element, that angle should be almost linear. Okay, so option B is our correct answer. You see again, hydrogen is between the 2 electronegative atoms. So option B here is the correct answer. Moving on to question number 23. The number of DD transitions expected for the complex is, so there is a copperamine aqua complex is shown. The copper is in a 2 plus oxidation state. So 2 plus oxidation state, the d electron configuration is D9. So copper 2 plus is a D9 species. So in a D9 species, and it is an octahedral complex, there are 6 ligands, 4 water ligand and 2 amine ligands. So in that case, it's an octahedral complex, and so for an octahedral arrangement, this is what an octahedral arrangement looks like: T2G and EG. So 6 electrons, d electrons in T2G, it is fully filled, and 3 electrons in EG. So it has one unpaired electron. There is one vacant site in the EG, in one of the EG orbitals. So we have to find the number of DD transitions. We have to figure out how many DD transitions are possible. So one would say there is only one, because there can only be one transition from the T2G level to the EG level. But that is not true, because in octahedral complex, especially in D9 species, the Yarn-Teller distortion comes into play. See, this is not a perfectly symmetrical. All the ligands are not identical. So if you arrange this, you can arrange the 2 amine ligands along the z-axis and the 4 ligands on the xy plane. So when you do that, there can either be a elongation along the z-axis or a compression along the z-axis because of the Yarn-Teller distortion. Now, either ways, the symmetry of this perfect octahedra is distorted, and you will find that because of the lowering of symmetry, that the complex becomes more stable. That is the driving force for the Yarn-Teller distortion. And this is the arrangement that you get. If there is a compression along the z-axis, the orbitals with the z element will get more destabilized, or they will get higher in energy. So here the dxz and the dyz moves higher in energy, and here the dz square moves higher in energy. So basically we have 4 energy levels. And if in the other case, if it is elongated along the z-axis, the complex is elongated along the z-axis, then the the orbital with the z components will be more stabilized, because along the z-axis the ligands are moving away. So those ligands with the z component will be more stabilized. So the dxz, dyz orbitals you see here moves lower in energy, and in the EG here the dz square moves lower in energy. So in either case, either whether there is a compression or whether there is an elongation, now we have 4 energy levels. Now because of these 4 energy levels, now you can expect 3 transitions, because an electron can either go from this dx square y square to dz square, or one of these EG orbitals, the xz or yz, to this dz square, or from the dxy to dz square. So basically you will find 3 transitions for this complex, and the reason why it is showing 3 transitions is because of the Yarn-Teller distortion coming into play. Okay, so option C, 3 transitions, 3 DD transitions is the right answer. Moving on to question number 24. The plot showing the magnetic behavior of oxy and deoxyhemoglobin is. So 4 plots are shown, and the oxyhemoglobin is shown in the solid lines. So the solid lines here, the solid lines represents oxyhemoglobin, and the dashed lines represent deoxyhemoglobin. So these dashed lines here, that is for deoxyhemoglobin. So now you have to find which is the correct plot for magnetic susceptibility and temperature. So there is a law called Curie's law, you might have studied, according to which for a paramagnetic substance, the magnetic susceptibility is inversely proportional to the temperature. So the magnetic susceptibility chi m is inversely proportional to temperature. If that is the case, chi m multiplied by temperature will be a constant. Correct? So magnetic susceptibility multiplied by temperature is constant. Now let's look at the case for deoxyhemoglobin and oxyhemoglobin. In deoxyhemoglobin, we know that in hemoglobin, the heme unit, there is a heme unit. There are basically four heme units in a hemoglobin molecule, and each of these four heme units consist of a porphyrin ring system with an Fe2 plus ion in the occupying the space in between within the porphyrin ring. And the ion is in the deoxyhemoglobin. When it is the ion, it's not oxygenated. It is in a high spin state. It's a D6 species, ion 2 plus D6 species, which is in a high spin state. So high spin state means there's four unpaired electrons. So if you look at the octahedral arrangement T2G and EG, so basically you will have one electron each. If you fill one electron each in each of these five orbitals, so the lowest orbital in the T2G there will be one paired, and then the other four electrons will be unpaired. So there are four unpaired electrons in Fe2 plus. That means it's a paramagnetic species. Deoxyhemoglobin is a paramagnetic species. Now once it gets oxygenated, once oxygen ligand binds to this ion, then it becomes diamagnetic. It's no longer paramagnetic. The electrons get paired, and then it becomes a diamagnetic species. So basically the deoxyhemoglobin is paramagnetic and oxyhemoglobin is more diamagnetic. So which one of this will have more magnetic susceptibility? Definitely deoxyhemoglobin, the paramagnetic species, will have more magnetic susceptibility. So the magnetic susceptibility, you have to be very careful what the graph is looking at, what the graph is plotted, what is on the x and y axis. See, on the x axis it is magnetic susceptibility multiplied by temperature. It is not a magnetic susceptibility versus temperature. It is magnetic susceptibility multiplied by temperature versus temperature. So some students might accidentally choose the option C, because they'll say, okay, the dotted line is for the deoxyhemoglobin. Deoxyhemoglobin is paramagnetic, and according to Curie's law, magnetic susceptibility is inversely proportional to temperature. So as we go increase the temperature, the magnetic susceptibility will decrease. But make sure what you see here, what is on the y-axis. See, on the y-axis it is magnetic susceptibility multiplied by temperature. Now magnetic susceptibility multiplied by temperature is a constant. So it both the curves for the deoxyhemoglobin and oxyhemoglobin should be a straight line, because for deoxyhemoglobin it is a constant. Magnetic susceptibility multiplied by temperature is a constant for paramagnetic species, that is the deoxyhemoglobin, and for oxyhemoglobin also which is a diamagnetic susceptibility, it is not affected by temperature. The magnetic susceptibility is not affected by temperature, and so that is also a constant. That is, the magnetic susceptibility curve was multiplied by temperature versus temperature will also be a constant for the oxyhemoglobin. So basically you will get two straight lines, right? But the magnetic susceptibility for the paramagnetic species will definitely be higher. So the dotted lines, the dashed line, which is the magnetic susceptibility multiplied by temperature for the deoxyhemoglobin, the paramagnetic species, will be higher. And for the diamagnetic species, the magnetic susceptibility is usually zero, or actually diamagnetic species show a negative, most often negative magnetic susceptibility is also mostly near zero. Okay, so option A is the correct answer. Option A. Okay, moving on to question number 25. 25, the major product formed in the following reaction is. So here a reaction, a reactant is given and a reagent is given. You have to predict the product. So if you look at the reactant, it is a halo species. It's an alpha halo compound. It's an alpha halo ketone, actually alpha halo, because on the alpha carbon you will see a halogen, and additionally there is also acidic alpha hydrogens on this compound. So a ketone with alpha halogens and alpha hydrogens, and the reagent is a base, sodium methoxide. It's a base. So if you have alpha hydrogens next to the ketone, those hydrogens are extremely acidic. So basically the first step would be to abstract the acidic hydrogen here. So you will form a carbanion here. So basically it's enol form. The negative charge can get delocalized to this bond, and the double bond O electron will get shifted onto the oxygen. So you will get O minus and a double bond here. So it is a keto-enol kind of tautomerism it can undergo. So this the further this charge, once the charge is on this carbon, it can attack this carbon here and form a bond here. So it will form a cyclopropane type of structure. Once you get the cyclopropane structure, then the methoxide, the base, again here it can attack on this carbon because the carbon will have a slightly positive charge and the oxygen is slightly negative. So the base here, so you see the sodium methoxide is acting as a nucleophile here, whereas here the sodium methoxide acted as a base to abstract the proton. So here it is acting as a base to abstract the proton from this the alpha hydrogen, and here the sodium methoxide is acting as a nucleophile by attacking this slightly positive carbon here. So once it attacks here, the double bond O, the pi electron shifts on to the oxygen, like here you will get a negative charge here and you will get OMe here. And then basically the next step is shifting of electrons. So this shifts back, forms the double bond O, and once it shifts back, this bond shifts back to here and the bromide is removed from this species, and you will get this particular structure. And now this rearrangement, it's a named rearrangement. It is called the Favorsky rearrangement, and this is one of the favorite rearrangements for the JAM question paper. This rearrangement as in different forms is asked every year in JAM question paper. So make sure you study this rearrangement really well. Okay, so with that we finish question number 25. The option here is obviously A. Okay, A is the correct option. Thank you.